In this lesson, we're going to take a look at how we can predict solubility. So if you recall, when we look at a solution that has something dissolved in it, an ionic compound is going to dissolve or dissociate into positive cations and negative anions. So the cations are going to be surrounded by the slightly negatively charged end, or the oxygen atoms in water, and the chlorine anions here would be surrounded by slightly positively charged hydrogen ends of water. We also looked, when we talked about solubility, at how much of something will dissolve in water. So we have sodium chloride here, and 35.9 grams of that will dissolve in 100 mils of water at 20 degrees Celsius. And calcium carbonate has only 0.005 grams that would dissolve in 100 mils of water at 20 degrees Celsius. So we would say that sodium chloride is soluble. And so when we write the formula for sodium chloride in an equation, we would say that if it's in water, it is aqueous. It is going to dissolve there. For calcium carbonate, on the other hand, because so little of it dissolves in the water, the vast majority of calcium carbonate that would be added to water would actually not dissolve. And so for that one, we would say that it's solid. So what we're going to use to help us determine if ionic compounds that are in water are aqueous, will dissolve in water, or will not, and therefore are solid, are the solubility rules. And there's a few different tables. This is one example of a table. So we have listed anions over here and cations over here. And we can see if the anion-cation pairs are soluble or low solubility. So anything that is soluble, we would say, is aqueous, and anything that is a low solubility, like calcium carbonate, we would then say is S, or solid. So for example, I have lead 2 nitrate here. So I'm going to look for, there's nitrate, and nitrate with most cations is soluble. So that means that in water it's going to dissolve and therefore be aqueous. Here's another version of a solubility table. So all of the pairs over here are going to be soluble, and then these are exceptions, and then anything that falls in here will be slightly soluble with the exception of those. So if I look for potassium iodide, so I can see chlorine and other halides, so the other halogens there. So they are soluble because they're over here, so they're very soluble with the exception of these. And potassium is not listed over here, so that means that this is going to be soluble, which means it's aqueous in water. Here's another version of a solubility table, and this is the one that you find in your data tables. So lead 2 iodide, so iodine is over here, and it is soluble with most things, low solubility with these, and lead 2 is one of those things that it has a low solubility with, and so this is going to be a solid then. It will not dissolve most of it. Potassium nitrate, so I have nitrates over here, and they are highly soluble with all. So this would then be aqueous. So that's how we use our solubility rules to decide if ionic compounds are solid. So remember, solid because they have very strong bonds, so there's no differentiation between intra and intermolecular. And so they have a very high melting point, which means at room temperature they're going to be solid. Now, the other thing we had learned about ionic compounds is that they are very good at dissolving. So this is how we are deciding which ones are indeed going to dissolve in water and therefore be aqueous if they're in solution, and which ones will just stay as the solid because they don't dissolve, or very little of it dissolves. Okay, so part of the point of this is to write molecular equations, and so those show all the substances, elements, or compounds using their formulas. They identify the state, so solid, gas, liquid, or aqueous. And so it's important to show the states in these equations. So if I take those 4 compounds that we just identified as either aqueous or solid, if I have those in a reaction, so lead nitrate reacting with potassium iodide produces lead iodide and potassium nitrate. So we'd found everything with the exception of lead 2 iodide to be highly soluble, and so those are all AQ. So lead 2 iodide was the one exception, and so that one was solid. So this is where we use them, and then we'll take a look in our next lesson at net ionic equations and where we go from here. So for now, though, we'll write full molecular equation with the states. So if I have fluorine gas bubbled through a solution of sodium chloride, so fluorine from Hofbrinkel is F2. Now I can use the periodic table to determine its state because it's an element, but I'm actually told here that it's gas. A solution of sodium chloride, and so that is a single displacement reaction. Because fluorine and chlorine are both halogens, we have our rules of reactivity where the higher up in the group we are, when fluorine is the very highest element in that group, the more reactive it is. So because fluorine is more reactive with chlorine, it is going to kick chlorine out and it is going to pair with the sodium to make sodium fluoride. And then we're going to have chlorine, which also Hofbrinkel, so also 2. So we need to find sodium chloride, sodium fluoride, and chlorine for states. So I have my chlorides over here, and this didn't work out well. Whoops. There we go. Okay, so sodium chloride. So chloride is low solubility with these. Sodium is not one of those. Everything else highly soluble. So sodium chloride dissolves. And then fluorides. So I have magnesium, calcium, barium, and lead 2 is low solubility, but with everything else it's soluble. So both sodium chloride and sodium fluoride are aqueous. And then I can use the periodic table to find out. So chlorine is blue, which is a gas. So I had fluorine, which was a gas. Sodium chloride was highly soluble, so it's aqueous. And then sodium fluoride was also highly soluble, aqueous, and chlorine was a gas. And to make this balanced, got 2 in front of each of those. So that is how we'll use the solubility rules to determine the states of ionic compounds. So remember, ionic compounds, we would say, are solid at room temperature because of the incredibly strong bonds, but then they're also very good at dissolving in water. So those solubility rules help us to identify which ones will dissolve in water and therefore be aqueous.